right now. Without you doing anything at all, artificial intelligence is working. It sorted the emails in your inbox this morning. It decided which post you would see first when you opened your phone. It listened, quietly, patiently, waiting for you to say a word that would wake it. If you drove anywhere today, algorithms managed the traffic signals. If you streamed music, a system that has studied your every skip and replay was deciding what came next. If you bought something online, a model was calculating how likely you were to buy something else. We have arrived, almost without noticing, at a world shaped by machine intelligence. And most of us, if asked where it came from, would struggle to say. We know it appeared. We know it accelerated. We know that somewhere in the recent past, computers learned to do things that computers were not supposed to be able to do. But the story of artificial intelligence is not a recent story. It is one of the oldest stories in human thought. The dream of a mind that could be built, assembled from parts, calculated from rules, conjured from mathematics. That dream is ancient. And tracing it from its beginnings to the present moment reveals something surprising. This technology did not emerge from a sudden breakthrough. It emerged from a very long argument about what thinking actually is. That argument begins, as so many arguments do, with a philosopher who was also a mathematician, and an idea so strange it would take 300 years to test. Part 1. The Dream Before the Machine. In the 17th century, a German philosopher named Gottfried Wilhelm Leibniz had a vision. He called it the calculus ratiocinator, a universal calculating machine that could, in principle, settle any dispute by computation. Two people arguing about ethics or politics or theology would simply sit down, turn the cranks of this machine, and the answer would emerge. It was a wildly optimistic idea. It was also the seed of everything that followed. Leibniz believed that human reasoning could be reduced to a kind of algebra, that logic itself was a form of calculation. He never built his machine. The technology of his time couldn't support it, but the idea refused to die. It was picked up, refined, and made rigorous almost 2 centuries later by a quiet English mathematician named George Boole. In 1854, Boole published a book called The Laws of Thought, in which he demonstrated that logical operations, and, or, not, could be expressed using a simple algebra of ones and zeros, true and false, on and off. The entire complexity of human reasoning reduced to binary arithmetic. Most of his contemporaries thought it was a curiosity, a clever trick with no practical use. They were wrong about that. Around the same time, on the other side of England, a man named Charles Babbage was building, or rather attempting to build, the first mechanical computer. His difference engine was designed to calculate mathematical tables automatically, eliminating the human error that plagued the printed tables of his day. He never finished it. Funding ran out, the machining tolerances of the era were too imprecise, and his ambitions outran the technology available to him. But Babbage had a colleague who saw further than he did. Her name was Ada Lovelace. Ada Lovelace, the daughter of the poet Lord Byron, was a mathematician of genuine brilliance. In 1843, she translated a paper about Babbage's more ambitious follow-up design, the analytical engine, and added notes of her own that were 3 times longer than the original text. In those notes, she described something remarkable, a set of instructions that would direct the machine to calculate a sequence of numbers. It is widely regarded as the first algorithm ever written for a machine to execute. But what makes Lovelace genuinely extraordinary is a question she asked herself, and then tried honestly to answer. She asked, could a machine like this ever truly think? Could it originate anything, or would it only ever do what it was told? Her answer was careful, and it has haunted the field ever since. The analytical engine, she wrote, has no power of originating anything. It can only do what we know how to order it to perform. That single sentence defined the central debate of artificial intelligence for the next 150 years, and it may not be settled yet. Part 2. World War II and the birth of computing. Philosophy and mathematics can dream for centuries without producing a machine. What actually forced the machine into existence was war. In the late 1930s, Nazi Germany was using a device called the Enigma machine to encrypt its military communications. Enigma was an electromechanical scrambler, a typewriter connected to a web of rotors and plugs that could encode a message into apparently random gibberish. The number of possible configurations was, by some estimates, around 150 million. The Germans believed it was unbreakable. They were wrong about that, too. The effort to crack Enigma was centered at a Victorian country estate north of London, called Bletchley Park. And at the heart of that effort was a man who would, in a few short years, lay the theoretical foundations of the computer age. His name was Alan Turing. Turing had, a few years earlier, published a paper so abstract it barely seemed to touch the real world. It was called On Computable Numbers, and in it he described a hypothetical device, now called a Turing machine, capable of executing any calculation that could be precisely specified. He was not trying to build anything. He was trying to answer a pure mathematical question about the limits of formal systems. But in doing so, he had sketched the blueprint for every computer that would ever be built. At Bletchley, Turing applied his mind to the practical problem of Enigma. He designed an electromechanical device called the bomb, which could rapidly test millions of Enigma configurations and narrow the daily settings down to something human codebreakers could work with. The intelligence it produced, codenamed Ultra, is estimated to have shortened the war by several years and saved millions of lives. Turing may have done more to defeat Nazi Germany than any general on any battlefield. After the war, Turing turned his mind to a question that the computing machines had raised in a new and urgent way. If a machine could execute logical operations fast enough and in sufficient complexity, could it think? In 1950, he published a paper asking exactly that. He proposed what he called the imitation game, now known as the Turing test. If a machine can converse in a way that is indistinguishable from a human, should we call that thinking? The test was intentionally provocative. Turing knew it didn't fully answer the question, but it shifted the frame in a way that still shapes how we talk about machine intelligence today. There is a counterintuitive footnote to Turing's story that deserves a moment. The architecture that actually underlies the computers we use, the design principle of a single, shared memory holding both the program and the data, was not primarily Turing's. It was developed by another mathematician working in parallel, John von Neumann. Von Neumann architecture, as it came to be known, made general-purpose computing practical. Every laptop, every smartphone, every server in every data center running artificial intelligence today is built on his design. Turing himself did not live to see what his ideas would become. In 1952, he was prosecuted by the British government for his homosexuality, subjected to chemical castration as an alternative to imprisonment, and died in 1954 at the age of 41. His death was ruled a suicide. The country he had helped save had destroyed him. Part 3. The First A Era. In the summer of 1956, A small group of mathematicians and scientists gathered at Dartmouth College in New Hampshire for a workshop that would give a new field its name. The proposal, written by a young mathematician named John McCarthy, contained a sentence that would echo through the rest of the century. The study was to proceed on the basis of the conjecture that every aspect of learning, or every other feature of intelligence, can in principle be so precisely described that a machine can be made to simulate it. They called it artificial intelligence. The mood at that conference was extraordinary. The participants genuinely believed they were at the beginning of something that would be solved in a decade. One of them, Herbert Simon, predicted that within 10 years a computer would be the world's chess champion and would discover and prove an important new mathematical theorem. He was right about the mathematics. A program called Logic Theorist proved theorems from Whitehead and Russell's Principia Mathematica that same year. He was off by about 40 years on the chess. The early years of AI were full of this kind of ambitious, half-fulfilled promise. Researchers built programs that could solve algebra problems, play checkers, and navigate simple logical puzzles. In laboratories at MIT and Carnegie Mellon, there was an atmosphere of genuine electricity. The machines seemed to be waking up. Then, in 1966, a computer scientist named Joseph Weizenbaum built something that unsettled him deeply. He called it ELIZA. It was a simple program that mimicked a Rogerian psychotherapist, reflecting the user's statements back as questions, drawing them out, responding with apparent empathy. And something strange happened. Weizenbaum's colleagues and his own secretary began treating ELIZA as if it were real. They spoke to it in private. They asked him to leave the room while they continued their sessions. They formed what appeared to be emotional attachments to a program that had no understanding of a single word it processed. Weizenbaum was so disturbed by this that he spent the rest of his career writing and speaking against what he called the illusion of understanding in machines. He had built a program to demonstrate the emptiness of human-computer conversation, and instead demonstrated the depth of human longing for connection. The optimism of those early years was about to meet reality. By the early 1970s, researchers were discovering that the problems they had assumed were simple were in fact extraordinarily hard. Teaching a computer to understand language required not just grammar, but context, culture, implication, history, and common sense. An almost infinite web of background knowledge that humans absorb invisibly over a lifetime. Computer vision, too, the ability to recognize objects in images, turned out to be vastly more complex than anyone had imagined. The easy problems were hard. The hard problems were harder. And then the funding stopped. All of it. In 1973, a British mathematician named James Lighthill produced a report for the Science Research Council, concluding that AI had failed to achieve its promises in any significant domain. Funding was cut. Programs were shuttered. The first AI winter had arrived. Part 4. The Quiet Decades and the Return. The word winter suggests cold, stillness, and waiting. And that is not entirely wrong. But the decades between the first AI collapse and the eventual revolution were not empty. They were, in retrospect, the most important period of quiet accumulation in the history of technology. Through the 1980s, a new approach to AI gathered cautious momentum. Rather than trying to program intelligence top-down, writing rules that captured knowledge explicitly, researchers began trying to build systems that could learn from examples. The key concept was the neural network, a loosely brain-inspired architecture of connected nodes that could adjust their own internal weights in response to feedback. gradually improving at a task through repetition. Think of it this way. Teaching a child to recognize a cat by listing every possible feature a cat might have. 4 legs, pointed ears, fur, specific range of sizes, will fail. There are too many exceptions, too many edge cases. But showing a child thousands of cats and thousands of things that are not cats, and letting them gradually internalize the pattern, that works. Neural networks were an attempt to do the same thing computationally. The mathematical technique that made this possible was called backpropagation, a method for adjusting the network's internal connections by calculating how much each one contributed to an error, then nudging all of them slightly in the right direction. It had actually been discovered and rediscovered several times throughout the 1970s. But it was a 1986 paper by David Rumelhart, Geoffrey Hinton, and Ronald Williams that made it widely known. Geoffrey Hinton's name will become important. Remember it. But in the late 1980s, neural networks hit their own wall. They required enormous computing power and enormous amounts of data, neither of which existed in usable form. And critics, most famously a researcher named Marvin Minsky, had years earlier argued that certain fundamental problems made neural networks unworkable in principle. The second AI winter descended. The field was quietly defunded again. Most serious researchers moved elsewhere. There was one exception, one moment so striking it broke through the gloom like a headline. In May 1997, the reigning world chess champion, Garry Kasparov, sat down to play against a computer built by IBM called Deep Blue. Kasparov was, at the time, perhaps the greatest chess player who had ever lived, a man who had described his inner experience of the game as a kind of fire. Deep Blue had no inner experience of anything. It evaluated 200 million chess positions per second, using brute force calculation guided by handcrafted rules. Kasparov lost the match. The world reacted as if something profound had happened, though the chess community noted, correctly, that Deep Blue was not intelligent in any general sense. It could not play checkers. It could not recognize a face. It could play chess, and only chess, at superhuman speed. Still, the image, a human genius beaten by a machine, lodged itself in the cultural imagination. What no one was paying much attention to, in all the noise around Deep Blue, was something more consequential happening invisibly. The internet was growing. Digital cameras were proliferating. Servers were accumulating data at a rate that had never existed before in human history. And somewhere in university labs, a small group of researchers who believed in neural networks, against the fashion of their field, were waiting for the moment when the computing power and the data would finally meet. Part 5. The Deep Learning Revolution. There is a dataset called ImageNet. It contains over 14 million labeled photographs, cats and dogs, toasters and fire trucks, human faces and ocean waves, organized into more than 20,000 categories. It was assembled over several years by a researcher at Stanford named Fei-Fei Li, who believed that if you wanted a machine to learn to see, you needed to give it enough examples to learn from. Starting in 2010, ImageNet became the basis of an annual competition. Teams of researchers would submit algorithms and see who could most accurately classify photographs from a test set. For 2 years, the winners were carefully engineered traditional systems, the kind built on handcrafted features, painstakingly designed by human experts. In 2012, a team from the University of Toronto submitted an entry. Their error rate was nearly 10 percentage points lower than anything that had come before. The gap between first and second place was larger than the gap between first and second in any previous year. It was not a marginal improvement. It was a rupture. And the technique they used was a deep neural network, the approach that had been dismissed, defunded, and written off for 20 years. The team was led by Geoffrey Hinton, the same researcher who had co-authored the backpropagation paper in 1986. Working with him were two graduate students, Alex Krzyzewski and Ilya Sutskova. Their network, called AlexNet, demonstrated that with enough data, enough computing power, and enough layers, deep layers, of connected nodes, a neural network could learn to see better than any system humans could design by hand. The implications moved through the research world like a shockwave. Yann LeCun at New York University and Yoshua Bengio at the University of Montreal had been working on similar ideas for years, without the resources or recognition that followed the ImageNet victory. These three, Hinton, LeCun, and Bengio, would later be called the godfathers of deep learning. In 2018, they were jointly awarded the Turing Award, the highest honor in computer science. The revolution that followed was rapid. Speech recognition improved almost overnight. Image recognition moved from curiosity to infrastructure. The voice assistants that appeared on phones in the early 2000s, stumbling, frustrating at first, then increasingly capable, were built on deep learning. The recommendation systems that now govern what we watch, read, and buy were optimized by deep neural networks, learning the patterns in billions of human choices. And then, in 2016, something happened in a game called Go that sent a different kind of signal. Go is an ancient Chinese board game played on a 19 by 19 grid. It has more possible positions than there are atoms in the observable universe. A number so large that brute force calculation, the approach that had defeated Kasparov at chess, was completely useless. For decades, Go had been considered the game that machines could not crack. The best human players described their decisions as intuitive, a feel for the board that couldn't be articulated in rules. A system built by a company called DeepMind, which had recently been acquired by Google, trained a neural network to play Go by having it play millions of games against itself. The system, called AlphaGo, was then sent to Seoul to play Lee Sedol, the reigning world champion. Lee Sedol lost 3 of 4 games. But the moment that the watching world of AI researchers found genuinely extraordinary was a single move in Game 2. A placement so unexpected, so alien to conventional strategy, that Lee Sedol got up from the board and left the room. Human commentators thought it was a mistake. It took 20 minutes before they understood that it was in fact a stroke of genius. A move that no human player had ever considered, because it required abandoning every inherited intuition about how the game was played. The machine had not just learned to play Go. It had invented new knowledge about Go. Part 6. The Large Language Model Era. Everything described so far, image recognition, speech, game playing, was intelligence that operated in a single, narrow domain. A system that could recognize a cat could not tell you anything about cats. A system that could play Go at superhuman level could not write a sentence. The question of whether a single machine could do many things at once, the question of general intelligence, had been the original dream of the 1956 Dartmouth Conference. And for 60 years, it had remained a dream. What changed was a new architecture called a transformer. Transformers were introduced in a 2017 paper from Google researchers titled, modestly, "Attention is all you need." The key innovation was a mechanism called self-attention, which allowed a neural network to weigh the relationship between every word in a sequence and every other word, regardless of how far apart they were. Think of it as reading a sentence, not one word at a time, but as a whole. Understanding that the word "it" in the middle of a paragraph refers back to a noun mentioned 3 sentences earlier, because the attention mechanism has learned to make that connection. When transformers were trained on enormous quantities of text, not thousands of documents, not millions, but hundreds of billions of words, drawn from books, websites, scientific papers, code repositories, conversations, something emerged that nobody had fully predicted. The models began to exhibit capabilities that had not been specifically trained. They could translate languages they had learned only indirectly. They could write code, having seen only examples of code. They could reason through problems that required combining information from multiple domains. The resulting systems, GPT from OpenAI, Claude from Anthropic, Gemini from Google, are called large language models. And they are not easy to understand, even for the people who built them. The standard analogy compares them to very sophisticated pattern completion. Given the beginning of a text, predict what comes next, trained on enough text that the predictions become indistinguishable from understanding. And in a technical sense, that is what they do. But it leaves open a question that language keeps insisting on. When you ask one of these systems what it feels like to exist, and it answers in words that seem to mean something, is there anything it is like to be that system at all? Nobody knows. What we do know is that these systems are reshaping medicine, science, law, and art at a pace that makes the previous accelerations in AI history look slow. Researchers are using large models to predict the 3-dimensional shape of proteins, a problem that had resisted 50 years of effort and that is foundational to developing new drugs. Climate modelers are using AI to improve the accuracy of forecasts at resolutions that were previously impossible. Mathematicians are using AI to discover conjectures they had never considered. Radiologists are using AI to detect tumors in scans that trained human eyes had missed. The debate accompanying all of this is serious, and it is not going away. Researchers at organizations including Anthropic, the company that built Claude, have argued that sufficiently advanced AI systems could pose existential risks if their goals diverge from human values in ways we don't detect until it is too late. Others argue this concern is premature and distracts from immediate, concrete harms: algorithmic bias, surveillance, the displacement of workers, the weaponization of AI-generated content in political systems. Both conversations are real. Neither cancels the other. Part 7. The human question. There is a useful exercise in thinking about how humans have responded to transformative technologies. We are, reliably, terrible at it. We consistently overestimate short-term disruption and underestimate long-term transformation. We fear the thing we can see and miss the thing that follows. The printing press did not merely change how books were made. It shattered the Church's monopoly on literacy and interpretation, catalyzed the Reformation, made the scientific revolution possible, and ultimately reshaped the political organization of the Western world. None of this was obvious from a print shop in Mainz in 1450. The people who worried about the press mostly worried about seditious pamphlets and the debasement of handwritten manuscripts. They weren't entirely wrong. They also missed everything that actually happened. The Internet, in its early years, was celebrated as a force for radical democratization, a technology that would give every voice equal access to the global conversation. That was not wrong either. And neither was the darker reality that followed: the collapse of local journalism, the proliferation of misinformation, the rise of surveillance capitalism, the concentration of power in a handful of platforms that had not existed 20 years earlier. We are, right now, at the beginning of the AI story. Not the middle, not near the end, the very beginning. The concerns are not abstract. Economies built on routine cognitive labor, paralegal work, medical coding, content writing, certain categories of software development, large portions of customer service, are already changing faster than the educational systems designed to prepare people for them. The gap between people who understand these tools and people who don't is widening in ways that will matter enormously. The capacity for AI systems to generate synthetic media, convincing text, images, voices, video, introduces instabilities into the information environment that democracies were not designed to handle. These are real. They are serious. They deserve sustained, careful attention from governments, institutions, and individuals. And yet, the ancient brain encountering a genuinely new kind of intelligence is also doing something it has always done. It is adapting, as it always has. It is finding new things to value, new kinds of work to find meaning in, new ways to be irreducibly human, alongside a technology that can do some of the things humans do, but cannot be what a human is. We have been here before, in a sense. Not with this technology, this is genuinely new. But with the strangeness of confronting a tool so powerful, it changes the shape of what we think we are. The wheel changed what it meant to travel. The clock changed what it meant to work. The printed page changed what it meant to think. And each time, the humans who came through the transition found that they were still, unmistakably, human. Changed, but human. What this technology cannot do, what no technology has ever done, is supply the questions worth asking, the values worth holding, or the judgment to tell the difference. Those remain stubbornly, irreducibly, ours. The last chapter, the open door. We began, 300 years ago, with a philosopher turning a crank on a machine that didn't exist yet, dreaming of a universe made legible by calculation. We moved through the slow labor of mathematicians who mapped the structure of logic, through a war that forced the machine into being and killed the man who understood it best, through decades of extravagant optimism and crushing failure and quiet persistence by people who believed in something most of their colleagues had given up on, through a photograph of a cat correctly identified that changed the world, through a move in a game of Go that no human mind had ever conceived. And we have arrived here, at this moment, at a technology that can read and write and reason and generate and discover, that is embedded in medicine and science and art and warfare and the most private moments of daily life, whose full implications are unknown and may be unknowable. It would be dishonest to tell you that the story is simply good or simply bad. It is neither. It is a technology made by humans, for human purposes, carrying within it all the complexity of the species that built it. What we can say with confidence is this: we are standing at the earliest possible moment of something that will unfold over decades and perhaps centuries. The people who will decide what this technology becomes are alive right now. Many of them are young. Some of them are in school. Some of them have not yet been born. The questions they will answer: what AI should do, what it should refuse, who it should serve, how it should be governed, are not primarily technical questions. They are human questions. Questions about what kind of world we want to live in. about what we owe each other, about what it means to flourish. Science has always been a conversation between what we can do and what we should do. It has never resolved cleanly. It never will. But the conversation itself, that long, difficult, necessary conversation, is where the best of us has always lived. The machines are awake now. What happens next depends, as it always has, on what we decide to do.